Let me give a harder example right now in our remaining few minutes. Remember that our formula to convert back and forth between continuous time and discrete time is this. And our other formula that's helpful is sampling time period is equal to 1 over the sampling frequency. So armed with that, let's create sample 1, signal 1, for which is cosine of 0.6 pi n. So in other words, our omega for this particular signal is going to be our omega sub 1, signal of 1, is going to be 0.6 pi. The omega is whatever is multiplying your n by. And this is in between our range of 0 to pi, right? It's just a little bit to the right of that range. So we're not going to mess with it much. I'm going to give a different signal, though, that's not in that range. And I'm going to call it cosine of 1.4 pi times n. And so that's outside of this range. And I'm going to try to bring it back in this range somehow. I'm going to say, you need to be able to do this, by the way, for tests and homework. I'm going to say that there's no difference between 1.4 pi and 2 pi minus 0.6 pi. That's the same thing, multiplied by n. The reason why I chose 2 pi is because when I do the subtraction, I get cosine of, if I multiply through here, I get 2 pi n minus 0.6 pi n. And now you know that I can add or subtract any multiple of 2 pi n, and I'm not changing my cosine because it's periodic in 2 pi n. So that's got to be the same as cosine of minus 0.6 pi n, right? You can add or subtract any multiple, even if they're different multiples every time, of 2 pi and not change your result. But remember that cosine is even, so cosine of minus x equals cosine of positive x, and so therefore this equals cosine of positive 0.6 pi n. And so even though this thing has a discrete time frequency of 1.4 pi, that's the exact same thing as having a discrete time frequency of 0.6 pi, which turns out to be the same as our first sequence. But the really important thing is to see how I reduced a discrete time frequency that's not in the unique range of 0 to pi into something that is in the range of 0 to pi. So although it's equal to, although here this second discrete time frequency is equal to 1.4 pi, it's also equal to 0.6 pi. Here's one other way that we can fold these frequencies over. If I have a cosine of 2.6 pi, here the math is even easier. In other words, omega 3 is equal to 2.6 pi. Here it's even simpler. We can say that's just the same as saying 2 pi plus 0.6 pi n, which is equal to cosine of 2 pi n plus 0.6 pi n. Since we can add or subtract any multiples of 2 pi without changing things, that's the same thing as saying 0.6 pi n. And so that means that that is also the same as having a discrete time frequency of 0.6, since this is what's multiplied by n. And even that is the same thing as our y sub 1 of n. So these are three apparently different signals, and they would be completely different signals in continuous time, but in discrete time, they're all the exact same signal because of something called aliasing, which is what happens when your frequency is not in that range, and it's equivalent to something that is in that range. Okay, that's it for the material. Any questions for me?
Are those middle steps necessary to show, or could you just subtract the 2 pi from the original equation?
Well, you're not just substituting one, you're not subtracting 2 pi, you're subtracting 2 pi n, right? You're not subtracting a single 2 pi. You're subtracting 2 pi from n equals 1, but you're subtracting 4 pi from n equals 2, 6 pi from n equals 3. So you need to somehow show that you're doing different numbers of 2 pi for every index.
Yes, sir. I got you.
But as long as you can just see that, yeah, you don't need to do all those intermediate steps.